and finish it later if you would like to. But now we're going to talk about, that is what I would call a regular discrete probability distribution. A regular discrete probability distribution, you would have no idea what the numbers were unless I gave them to you. You have no idea how many televisions they sold or what the probabilities were, right? You had to be given the data. Back here you were given this data, and you could turn you were either given a frequency distribution, like I gave you here, and we turned it into a probability distribution, or in the question you just did, you were given a probability distribution, right? It gave you the probabilities right off the bat, and then you can do the work. They could have done, they could have like one number missing, like if they had this number missing here, you'd have been able to complete the table knowing that it had to sum to 1, correct?
Yeah.
If one number's missing. But basically they've got to give us these numbers because we have no idea what they are otherwise. So now we're going to talk about two special probability distributions. This one I'm sure you've all heard about. What do you remember about a binomial probability distribution?
Isn't it a success or fail?
A success or fail, okay? Anybody else remember anything about binomial distributions? So success or fail, right? Each trial only has 2 outcomes, usually considered a success or a failure. So let's say I'm thinking of opening a doggy bakery at the mall. And I go to the mall and I ask people who go by, do you have a dog at home? If you say yes, to me that's a success because you might be a potential customer. And if you say no, I'll be like, oh, that's a failure, right? And I would like to record that. That could be, when I say, do you have a dog at home? That could be a binomial experiment. The 4 properties for a binomial experiment is the experiment has identical trials. When I ask each customer who's at the mall, but if Brandon's there with his mother, I wouldn't ask them both. You know why? Because the trials are not independent. The fact that Brandon says, yes, I have a dog at home, would mean that his mother has a dog at home if Brandon still lives at home, right? So those trials would not be independent. So the trials have to be independent, the probabilities can't change, there has to be 2 outcomes, a success or failure, okay, identical trials. If I ask the question, hey Chris, how many dogs do you have at home?
0.
0. Colton, how about you?
1.
1. Mylene? None. Kara? 0. Brandon?
1.
1. Okay. I have 2. I have 3. My favorite one. See my favorite dog ever. I have 2. Can that be a binomial experiment? If I say how many, who's anyone got more than 2 dogs? Okay, how many do you have? 3. How many?
4.
4. Okay, anyone got 5? Okay, this cannot be a binomial experiment. Why? Was there 2 outcomes? Right, until I said 2, you guys always said 0s and 1s, so that's why I said I've got 2. And you got 3 and you got 4, right? Because, I mean, it could be that Ryan's really a dog hoarder and he's not saying anything and he's got 99 at home. You know, it's like, when you stop someone, you've no idea. They could say, oh, well, I'm a breeder, I've got 57 at home, you know? So, when you ask, if I ask the experiment, how many dogs do you have at home? That's not binomial. But if I say, do you have a dog at home? You can only say yes or no. That's a binomial because there's only 2 outcomes, a success or a failure. Right? So that's kind of how you can tell if something's a binomial experiment. The thing about knowing something's a binomial experiment is all I have to give you is n, my sample size, and p, the probability, okay? And I can ask you to come up with a probability distribution. So for example, if I said to you, I'm going to go to the mall. I'm going to stop 3 people, because I don't want to write 30 people out. So I would never open a business based on asking 3 people. But anyway, we're going to pretend. N is 3. I'm going to ask 3 people. According to the American Humane Society, 60% of people have dogs at home. 63 or 64, I think. But 60% of people have dogs at home. Okay? If I could ask you, just having given you this information, I can say to you, make me a probability distribution. Okay? So a probability distribution, remember, is list all the possible values of X and their probabilities. What are the possible values of X? Very good. 0, 1, 2. Most people want to say 0 and 1 because they remember each trial has 2 outcomes. Brandon can say yes or no. Chris can say yes or no. Colton can say yes or no, right? Each trial has only got 2 outcomes. But if I stop 3 people, the random variable that I'm measuring is how many yeses are there? How many successes are there? You can all say you don't have a dog. Did you have a dog?
Yeah.
One, you did not. You did. So I got 2 yeses and 1 no, right? So I got 2 yeses. But I could have gotten none, and I could have gotten 3 yeses. So the possible values of X in a binomial experiment are from 0 to what is the general rule? N. Okay. The possible values of X in a binomial experiment are from 0 to N. If you have identified something as a binomial experiment, you can have much faster ways of calculating, for example, the mean. Remember what we did just now to get the mean? You had to do X or Y times F of Y or X times F of X and then sum the column L3. If I stop 3 people at the mall and 60% of people have dogs at home, if I stop 3 people, how many do I expect to have a dog at home? 2? Exactly, and how many do I expect? 1.8, right? Can't be 1.8, but that would be the mean. How did you get 1.8? You did 3 times 0.6. 3 times 0.6. That's the mean. 1.8. 60% of 3 is 1.8, right? You didn't have to do an X column, an F of X, and X times the F of X. You could. You will get the mean or the expected value, but you don't have to. So on a test, if I give you a binomial question, I'm expecting you to go 3 times 0.6 is 1.8, and it should take you about 15 seconds to do it at most. But if you did all this, it might take you 3 to 5 minutes, you're going to run out of time. You're not supposed to do this if you can do this. Okay. All right. So we're always interested in the number of successes, and that, in my case here, that is getting a dog. If you want to flip a coin and you consider a head a success, okay, your values of X is 0, 1, 2, and 3. This is ugly looking formula, but it's the binomial probability function. This part here should look familiar. What does it remind you of?
Combination?
Combination formula. This is the combination formula. So we can calculate these probabilities. I'm going to erase this because I don't need more space. Okay. So if I want to calculate these probabilities, these are not all equally likely, right? You told me the mean is 1.8, correct? So I would tell you that the number closest to 1.8, which in this case is 2, will have the highest probability. And this is furthest away, it will have the lowest probability. because this is, the mean's supposed to be the most likely. So how do I calculate this probability? In my calculator, I put 3, then I go get NCR, and I put 0, because I'm doing 0. Do that in your calculator. Right, 3, math, probability number 3. That's 1. Times P, which is 0.6 in this case, raised to the X, which is 0, so that right now this is 1. This is also 1, right? Anything raised to the 0 is 1. So I've got 1 times 1 is 1, times 1 minus P. So 1 minus 0.6, which is 0.4, raised to the N is 3, minus X. So this is 0.4 cubed. What is that? .064. If there's 60% of people have dogs at home, and I stop 3 people at the mall, there's a 6.4% chance I will get 0 people with dogs. Anyone have trouble putting that in their calculator? This is 3. Go math, probability number 3, then you put 0, you should get 1. Multiply that by 0.6 raised to the 0, you should still get 1. Multiply that by 0.4 cubed, you should get 0.064. When X is 1, we're going to do 3 NCR 1 times 0.6 to the 1 times 0.4 squared, because this is 3 minus 1 now. What is that? If I sum this column, what do you think it sums to? I have a probability distribution now. My values of X are 0, 1, 2, and 3, and these are my probabilities. I could say to you, what's the probability at least one person? You stop 3 people at the mall. 60% of them have dogs at home. When you stop 3 people at the mall, what's the probability that at least one person has a dog at home? What would you say?
28.
At least one. What does that mean? Huh? Could be more, right? Let's say there was a dozen donuts left in the break room. I ate at least 1. What does that mean? I might have eaten all 12, right? I 1 or more. At least 1 means 1 or higher. So what's the probability? What's the probability X is greater than or equal to 1? Would you add these together? 0.936? Or you could have done 1 minus this. That's why I can do it in my head. I didn't add these 3. I just did 1 minus that's 0.936. Okay, 1 minus that equals the same as that, correct? And that's what you need to get really used to, that relationship, because I'm going to give you a whole book of tables. Questions about this? We'll do one together over here. Alright, so I told you that if you know it's a binomial distribution, you can, for the expected value, know that it is just n times p. I want to prove it to you. Okay, so the expected value, right, is the same as the mean. You use mu if you have population data. You use x bar if you have sample data. It's the sum of x times f of x. So these are my f of x's. This is x times f of x. X is 0, so this is 0. This is 1 times 0.28. This is 0.864. This is 0.648. If I add this together, it adds to 1.8. This works. This method works. That just takes a lot longer than going 3 times 0.6. So with binomial, if you can identify your experiment to be a binomial experiment, okay, you have shortcuts in doing the expected value. You also have shortcuts in the variance, because remember we did x minus the mean squared, x minus the mean squared times f of x. The sum of this, I know you can't see this now, is the variance. Isn't that what we just did over here? The sum of that is the variance. But the variance in a binomial is also n times p times 1 minus p. It's 0.72 in my case. It's just n times p times 1 minus p. N is 3, p is 0.6, 1 minus 0.6 is 0.4. And then if I want the standard deviation, it would be the square root of 0.72. That's a lot faster than that table. When you have a regular discrete probability question like we had up here, you have to do the table. When you have binomial, you don't have to do the table. Martin Clothing Store estimates the probability a customer will make a purchase is 30% based on past experience. Generate a probability distribution for the number of customers that make a purchase out of the next 3 that come in. Okay, so none of them might make a purchase, all 3 might make a purchase, or anywhere in between. So you would do what we did here. 3, combination 0. In this case, the probability is 0.3. So 0.3 to the 0, 1 minus 0.3 to the 3 minus 0, and you would get these numbers. Okay? Anybody have questions about that before I give you a table? No. So you turn to the first set of tables. At the top, it says individual binomial tables. Can you see that? Okay, let's look at the one I did on the board. Okay, n was 3 and p was 0.6. So in the very first column, you go down to n is 3. Got it there? Then across the top, you go over to 0.6. And you can see in the second column, it gives you the values of x, right? 0, 1, 2, and 3. And then you should see the exact numbers that we calculated here. They go to 4 decimal places, so they have an extra 0 on the end. But they have 0.0640, 0.2280, 0.4320, 0.2160. Does everybody see that? Okay, let's look up these ones. N is still 3. But now p is 0.3. You get 0.3430, 0.4410, 0.1890, 0.0270. Does everybody see that? If you have a binomial question on a test and you are able to use your booklet, I'm expecting you to use it. I'm not expecting you to write out the formula. So what I do want you to write, because there are a lot of numbers, and sometimes students start writing here and then they go over and they skip something. I want you to write N is 3, P is 0.6, used booklet. And then I go and I'm like, well, she's wrong. I'll go and say, oh, she went to 0.65. And she copied down the wrong column. Do you know what I mean? So at least I know that you knew what you were doing. Because else, if I just get wrong answers and I have no idea what you did wrong, I'm not willing to look through this booklet trying to figure out what numbers you copied down, because there's too many numbers. So if you tell me what you tried to do, I will try to follow along. So you can use the booklet. When can't you use the booklet? Well, this booklet is not that thick, because it only goes up to N is 20, and then it goes to N is 25, and then it doesn't give you any more. So if I give you a binomial question where N is 40, you can't use this, because it's not in here. If I give you a question, they also have the probabilities of 1%, and then they go in 5s, 5, 10, 15, 20. So if I said the probability of something is, P is 32%, or if I told, that's why I did 0.6, it's really 0.64, you wouldn't be able to look in here if it was 0.64. Okay? So this can only be used at certain times, but if you can use it, I'm expecting you to use it. I'm going to give you a new copy of this to use during the exam. So no writing notes, I mean you can write notes in it, but you won't be using this on the test. Okay, so after the, oh, it's 1:15, all right. I'll save that exciting news for next time. Remind me we're working on the practicing with the booklet when we come in next time. Please clean off your boards. And if you're going to DECA today, DECA's at 3. With Matt Johnson, an ex-SEC DECA person who's now a worker at Wells Fargo.